Pay Attention to MLPs is a research article by Google Research and Brain Team released in June 2021. This article mainly focuses on putting the focus of researchers back to multilayer perceptrons, and basically the new variant that is introduced in this article called GMLP, which basically means MLPs with gating in this article. And the objective is to propose an alternative architecture that basically competes with the transformers. That is perhaps the most well-known machine learning model in key language and vision applications. And I want to show that this new model also operates as good as transformers. As we read through the paper, we understand that one of the other main claims is that the self-attention in the transformers is actually not critical for vision tasks. And this is the result of the fact that GMLP can achieve the same accuracy. They also show that GMLP even beats BERT in some language modeling downstream tasks. The whole objective of the paper is to basically show and demonstrate that multilayer perceptrons that have been considered relatively basic neural network models, if used correctly, can achieve results on par with most advanced models such as transformers. Now let's go through the introduction section and review some of the most important points that are mentioned in this section. Well, the first thing that is mentioned is the seminal work of transformers that have largely replaced LSTMs and recurrent neural networks that used to be the default architecture in natural language processing tasks. And also the fact that attention-based models are becoming pretty prevalent in computer vision tasks such as detection or recognition, as well as a good alternative to convolutional neural networks. Now, what are the main components of the transformer model, and what is exactly the secret to its success? So, transformer model combines two important concepts. First of all, unlike the autoregressive models such as recurrent neural networks, a recurrent-free architecture that transformer propose allows parallel processing of individual tokens. And the second component is how it aggregates spatial information across the tokens, which is basically done by the multi-head self-attention. Now, when you have attention mechanism to aggregate spatial information, what that means is that you're saying the spatial interactions should be dynamically parameterized based on the input representations. This means that basically when you have something like a self-attention component in the transformer model, you are basically intuitively putting it there to kind of allow a better representation of the spatial information across the different tokens. While it is also worth mentioning that multilayer perceptrons and fully connected networks with static parameterizations can represent arbitrary functions, and it is a known fact. Which brings us to this important question. Considering the self-attention as an important component of the transformers, the question is, how important exactly are these? And analyzing the necessity of self-attention modules is one of the key components of this article, as well as proposing an MLP-based alternative to transformers. By utilizing spatial projections and combining it with multiplicative gating, they have proposed the gating-based MLP or GMLP, which, as we will see, performs very well. When it comes to utilizing transformers for vision tasks, here are some of the important works. There's vision transformers, there's DIT, and now, as another alternative, there's GMLP. Another MLP-based approach was the MLP mixer, compared to which GMLP is around 3% more accurate with 66% less parameters. All in all, this work, as well as some other works that I mentioned here, questions the necessity of the presence of self-attention in vision transformers. When it comes to language modeling, the task of masked language modeling that was used in BERT is also pretty famous. GMLP is used for this task, and the result is that it is as good as transformers at minimizing perplexity. And one other finding that is presented in this paper is that perplexity is only correlated with model capacity and not very sensitive to the presence of self-attention. As they mention here, is pretty important because it indicates that the scalability of GMLPs is also as good as transformers, even though the self-attention module does not exist in them. The setting that was used for training was a 256 batch size, 1 million step training, and resulted in 87.7% accuracy on MNLI and 82.1% F1 on the Squad version 2. When it comes to fine-tuning, however, transformers have done a little bit better than GMLPs in the original format. And this happened on tasks that required cross-sentence alignment. Now, there are multiple ways to handle this, as is shown in this paper. One of them is basically by scaling the GMLPs or making them substantially larger, or utilizing a more of a practical solution, which is basically blending in a tiny bit of self-attention or having a very small, tiny self-attention module. And that will help to close the gap. All in all, the article suggests that self-attention is not a necessary ingredient for scaling up the machine learning models, and whether or not its presence is useful depends on the task at hand. Now let's discuss the GMLP model. Let's consider an example with the sequence length of n. When you have the representations, there are going to be a matrix X with these dimensions. Now here's what happens to X. First, you're going to use one linear projection, U, and as for its sample dimensions, for the BERT base, it is a 768 by 3072 matrix. So this multiplication will happen, and then a nonlinearity, such as GLU, will be applied on it, and this will give you Z. Then something is going to happen to Z that allows you to basically aggregate information from different positions without it, explicitly having to do something such as positional encoding. And then there will be this, which will be followed by another projection, which will give you Y. And with regards to the dimensions of V, again in the case of BERT base, it's going to be 3072 by 768. Now for a second, consider this one. If you consider that this be an identity mapping, what you're going to get is that you're going to get this. Which will reduce this pipeline to a normal, fully connected linear layer. So this will become a traditional feed-forward neural network. However, the idea is to choose and design S in a way that allows modeling complex spatial interactions across different tokens in your input. They are using the same protocols as BERT and as VIT for vision and natural language processing tasks. A good example is brought here, which means that, for example, when fine-tuning a language tasks, they concatenate together multiple text segments followed by padding, and then the predictions are done using the last layer representation of a reserved symbol, trying to avoid having too many confounding factors in the experiments. Now, having that n by dx, you want to do something about the spatial dimension. The most simplistic approaches would be to basically go ahead and design another linear layer for that, which means that you would have this function that this time multiplies this trainable matrix W from the left with Z plus B. And it's going to be a bias, and we will see that it's kind of important to decide what kind of initialization to use in this scenario. Now in this case, W is going to be a symmetric matrix from R n by n. And this B here is going to be token-specific biases. Now, SZ is defined in this paper as this. This means first you kind of find a gating mechanism that is basically generated by this trainable FWB, and you use that with element-wise multiplication to gate Z. As for the initializations, they have mentioned that it is practically beneficial to initialize W to close to 0 values and B to close to 1s, so that initially this gating becomes an identity matrix or an identity transformation, so that the model learns to kind of integrate the spatial information gradually. Another thing that they have found that could be effective is to split Z into Z1 and Z2, and then basically define SZ such as Z1, the representations to be gated, and another portion of those representations be used to find these gating mechanism. Also, normalizing the input to FWB have helped them in practice. Overally, this is called Spatial Gating Unit, or SGU. With regards to the connections of this definition with what is already there in the literature, they have this paragraph here. SGU resembles gated linear units, as well as some of the details in the earlier works, for example, the hybrid networks or LSTMs and RNNs, as well as squeeze and excite blocks in terms of basically utilizing element-wise multiplication. But it should be noted that SGU does not contain cross-channel projections and it does not enforce permutation and variance. Here's what is important here. The spatial projection in SGU could in theory learn to express superficial depth-wise convolutions. This means that you do not have to have channel-specific filters. Again, in that N by D notation, this would be the spatial dimension and this would be channels. This means that this single transformation that SGU learns can be shared across different channels. Looking at SGU, you can see that you can basically utilize that as an alternative to represent high-order relationships. For example, you have second-order interactions possibly captured in SGU. Well, looking at the self-attention, you have third-order interactions. And here are its orders of complexity compared to dot product self-attention. Now let's go to the implementations and the results. The first task they consider here is image classification, which they have tried to tackle without any use of extra data. Similar to some of the previous models, the image is going to be converted into 16 by 16 patches. And GMLPs as well as transformers drastically overfit the training data when it comes to image tasks. So it is important to regularize them effectively. Again, to avoid having confounding variables, they have used similar regularization recipe as the one used in DIT. And the hyperparameter that they have is the strength of the stochastic depth. Table 1 showcases the architecture specifications of GMLP models that are used for vision tasks here. Now let's look at the results. The findings here are that GMLPs are getting results that are comparable to DIT and VIT. So we have now an alternative to self-attention-based models that can be as data efficient as those when it comes to image classification tasks, surpassing all of the currently proposed MLP-like architectures. Figure 3 visualizes the spatial projection weights in the GMLP. Each row here is going to show some of the filters after being reshaped into 2D. We can see that there is a notion of locality that can be observed in these filters here. Now let's go through the natural language processing component of this work and the task of masked language modeling with BERT. So the task at hand here is MLM, or masked language modeling. Again, the protocol follows the traditional BERT. Well, there is an interesting result that they also report, and that is the fact that they have found that it is unnecessary to try to mask out pad tokens because GMLP quickly learns to ignore them. Pad size of 2048, maximum length of 128 for 125,000 steps. Over this dataset has been used for the case studies and ablations. And the main results are also with this configuration. Their experiments with the masked language modeling task showed that GMLPs tend to always learn tuplets-like matrices, which suggests that GMLPs are capable of learning the notion of shift and variance, which is implied by the MLM task as well. Later on, they try restricting W to be tuplets-like matrices as a form of regularization, given the fact that whether they do it or not, W will be tuplets-like matrix after some learning and doesn't really impact the quality. Now here are the baselines that they have used for ablation studies. The first one is birthed with a transformer architecture and learnable absolute position embeddings. Then they have birthed with a transformer architecture and T5 style learnable relative position biases. The third one is basically removing all content-dependent terms inside the softmax and only retaining the relative positional biases, which can also be viewed as a random synthesizer, and is a variant of transformers without the use of self-attention. And the fourth one is the MLP mixer, in which the multi-head self-attention module and transformer is replaced with a two-layer spatial MLP, which was a model that was originally proposed for vision tasks, but it is used here for the mass language modeling task. In terms of perplexity, the result is that SGO outperforms other variants, achieving perplexity values comparable to that of transformer, which are brought here, as well as some visualizations of the spatial filters. As you can see here, several versions of GMLP are used and tested. Now there is a case study for analyzing the behavior of GMLPs as the model size increases. Now, when it comes to counting the number of layers of the transformer, they have written this n+n format because they are mentioning that you have the self-attention and you have the feed-forward neural network in a single attention block, so you will have like a 6x+6 layers when you're trying to compare it with, for example, a sort of fully connected layer GMLP, which has 18 layers. And you can see that the number of parameters to compare are also pretty close to each other. And you can see that the gap between the perplexities are also sort of closing up as the models get larger. Figure 5 also indicates that. Now there's another point here. Even though GMLPs outperform transformers on SST2, they do worse on MNLI task, which has certain implications. When you have the MNLI task and you have transformers operate better, this sort of leads to believe that just outperforming in terms of perplexity doesn't necessarily mean everything. And the fact that as you scale the models up, the gap between the transformers and the GMLPs get closed, indicates that you can enlarge the model capacity to kind of deal with this issue. But there is a more practical solution, which is in section 4.3, and that is the use of tiny attention. The previous task on which GMLP operated better was a single sentence task, whereas MNLI is a sentence pairing task, which leads the authors to suspect the role of self-attention on these types of tasks. So GMLP itself is already capable of capturing spatial relationships. To improve it, they add an extra self-attention module that actually is not heavy, meaning that it just has a single head with a size of 64, and they call it AMLP, A for attention. And the result is that attaching this tiny bit of attention is sufficient to close the gap. Now going to the main results, they have used a full English C4 dataset and a common mask language modeling setup with this configuration, and the results again show that GMLPs are competitive. Here are tables 5 and table 6. Table 5 showing the model specifications and table 6 showing the results. Here, what they have done, which is interesting, is also this part, showing that you can actually scale this GMLP to be very large and then using it to outperform the BERT large on certain tasks without any self-attentions, even though this comparison is kind of unfair because of the difference in the number of parameters. Again, is a proof that MLP-like models can be competitive. All in all, this work suggested that there is a simpler alternative to the multi-head self-attention layers in transformers, and they have succeeded in putting the attention back on the traditional multi-layer perceptron-based models.